start. I'll wait 1 more minute. So the list is somewhere. This is my backup. Okay, it's just about time, so I will start this lecture. So welcome, my name is Antti Piironen. As you may already know, I'm going to teach you something about the digital signal processing. Okay, and this implementation is kind of extended classroom version. Welcome. And basically it means that all of these lectures and start of the lab sessions will be recorded for later viewing. Okay, so I think everybody has found the web page of the course, have you? If not, you can access it simply, let's see, users.metropolia.fi, then my username Antti KP, 2 T's, 1 I, KP, and I think it's DSP, either lowercase or uppercase, I don't remember. And I don't know if it actually makes any difference. Uppercase, yeah, it does make difference. Yeah, so DSP, like digital signal processing. Okay, which actually is just a link to that page, which is on Google Documents, open for anyone who has a link. All the material here, what we have is, well, it's Creative Commons licensing, so don't make money with that, it will be okay. Just give me some credits if you ever use that material for anything, you know, other than school. So everything will be on that page, so make a good note on that one. For example, the course syllabus. Okay, let's see if the clicker works. Digital signal processing, it has learning outcomes, it has recommended preliminary studies. So basically, what they are, so basically it would be nice if you knew the fundamentals of discrete mathematics and complex numbers, fundamentals of MATLAB or similar, and similar here means Octave. Programming, well, any language. MATLAB has its own kind of language, so we will learn by doing. How many of you actually have used MATLAB before? Excellent. The rest of you will learn. If you want to install the MATLAB on your computer, it's available on Amazon Bookstore for student pricing, I think. But there's also the free version Octave, which is a GNU project. So you can use either or. The exercises can be done with both of the tools. I will be using MATLAB here just because I couldn't get the graphics of Octave working on this new installation. Okay. Course contents, don't worry about that one, since that's actually something that someone else put there. Say 80% of that one will be on the course. There are also something that is not here, and that 20% is probably has less emphasis at least. Okay. Then about the learning environment, what you should have is the computer with audio. Okay. So here we probably have some audio on this computer maybe, but you can also use your laptops. It's actually a good idea. Then you can continue working on those exercises at home. And then, of course, you need the tools, MATLAB or similar, and then Google account. Is there anyone who does not have a Google account? Okay, good. That was a question for the rest of the world, you know. Still someone without Google. Okay, books. I have brief notes. But there are some books, real books. Sanjit K. Mitra has made really nice digital signal processing, a computer-based approach, which is excellent book for ICT student. So it's engineering manual, basically. And it also comes with some MATLAB exercise books and that kind of thing. So if you like books, that's a good one. If you like e-books, then there's a free one. Stephen W. Smith has made also a really good a scientist and engineer's guide to digital signal processing, very practical book. And he has also put that one on the internet, basically for anyone to either download it or look it online for free. Okay, and of course then the course web page, you cannot survive with that. Assessment criteria, active attendance and sharing. Okay, I will probably explain it later, what the sharing means. Continuous assessment of MATLAB exercises. And then there's an individual problem-solving project. Depending on how many students actually will end up in this course, it might be a group effort. But anyways, there will be a project. All right. Yeah, and doing well means you get 3, and doing excellent you get 5. Doing just, you know, with the left-handed or right-handed, if you are left-handed, then it's 1. And in between. Okay, so implementation, as I said, this is actually a kind of funny implementation. For Metropolia students, it's 7 weeks hard work. So 5 credits in 7 weeks, it's not easy. It's 135 hours of work. Okay, so if you have a full schedule before, now you know that you need to also fill some of your own time there. But there's also calculations how it's actually done. So everything is on course web page. This attendance on the labs and lectures is optional, but highly recommended. Okay. Yeah, and yada yada yada, blah blah blah. And there's the how this student workload is done. So lectures we have 7 times 2 hours with breaks. MATLAB lab exercises 5 times 4 hours. So we have 5 exercises, and then there's the rest of those lab hours are for the project work, and that self-study is about 45 hours. That's just to match the 135, which is 5 credits. And exam, there's no exam. Since I believe strongly on the continuous evaluation. Unless, of course, for online students, if the sometimes university requires exam, then you will have exam. Don't worry. Okay. Yeah, and those are the partners who are also with us. So next week, Vilnius starts next week. Chitkara starts probably this week, but due to the time difference, they will start, you know, using the recordings. Then there's Alcala University. Their semester starts 2 weeks from now. Then the SEIA, they will start 1 month from now, and so on. And yes, you can take pictures. Thank you for asking. Although it's not necessary since everything is available on internet. Okay. Good. So today we basically go through, oh yeah, there are some other links also there. For example, there's also enrollment link. Don't worry about that. Metropolia students have already enrolled, or I will enroll based on the information in that sheet using Vinha. That's mostly for the those outside students, our partner students. They don't have Vinha. Lucky them. Okay. And then also the teachers manual is actually for the online teachers. Course global schedule, you don't need to worry about that either, basically because all the deadlines and such kind of things are on the main page. That's for helping the abroad students. And then online sessions, that's actually a broadcast. So if you feel sick at home on Monday morning for some reason, you guys don't laugh at all. Mondays it can happen. Okay, for students, I have heard, then you can actually entertain you by looking at the online video broadcast, so get everything at the same time as the other ones. Yeah, and after that, after each session, the same day there will be also these videos are put into piece, so repository or depository, either or. Okay, good. So let's start with the first thingy, which is the general information. And let's see, I may actually have the similar kind of stuff also here. Okay, DSP theory. Just a reminder, as I said before, this is brief summary. It does not replace a good book or good online book or good anything. This is brief notes. It just basically summarize the topics. Okay, so yes, please come in. Enough seats. Okay, there you go. Okay, and of course, yeah, that's the important. This work is licensed under Creative Commons license. Whoa. Okay, there's latency. So, okay, we already covered that one. Motivation. How motivated are you? Digital signal processing. It's a hard topic. I know it. I have paid my price on this hard topic. But it's also practical and useful topic for ICT students. This should be on every single one's curriculum, but on the other hand, there are so many other things that should be on every ICT student's curriculum. So I would say this is one of the nice ways that you can specialize on something. Okay, so digital signal processing. Especially if you are embedded systems engineering major or software engineering, or actually even mobile systems, since this is the place you start actually banging your head on the later on the course on the this how fast you can get a small processor to go. Okay, what kind of things can be done? Thinking of the current technology, I have this is low scale Samsung J5, so with 8 gig of memory, which is way too low. The new one has more. But anyways, this phone has capacity for calculation about the same amount as so-called supercomputers in 90s. Or supercomputing workstations. Okay, and what we can use these. Not even a fraction what those supercomputing workstations could do. So I would say there's something wrong with the efficacy of the programs. Okay. This might be actually mandatory course for you. I don't know. For smart systems engineering, I think it's marked on the syllabus, maybe. Or you need this because someone told you to come here. Interesting? Yes, definitely. This is interesting topic. My first encounter with the digital signal processing was, of course, in my own university, which is now called University of Eastern Finland. So at that time it was Joensuu University, and there was a crazy professor who told, how about this signal processing? It looks like a really good rising topic on the field of applied physics. And that was year 1986. Okay, it still is, you know, a promising topic. And I have found absolutely no days that would be boring with working on the digital signal processing. Oh, there are more sheets. There you go. You don't have to stand, unless you want, of course. But don't stand on that side of the table, since that's expensive. Okay. Yeah. And this is also the place that some students have always found, oh, okay, that's why we need these mathematical tools. Digital signal processing is laying heavily on the mathematics, but on the practical side of the mathematics. We don't use nabla or epsilon here unless you want to, but then this is probably not the right course for you. But anyways, that's a tool, like a hammer for a carpenter or knife for a carpenter. So it's a tool for digital signal processing. Very practical tool, actually. And of course, well, who doesn't want to create your own phone ringing tone that absolutely no one else will have or don't want? Okay. Yeah, you need some math. I have asked Timo, Salin, to help you with the math on some sessions if needed. So you are in good hands. Okay, those are the topics, but anyways, this might still change, the order might change. This is somewhat the topics what we will be covering. We'll start with digital signals, what actually they are. Then we go to digital system fundamentals. So this week is for signals, next week for systems. Then we go deeper into system responses. And on fourth week, that's the plan right now, we go to very practical topic called filter design. Okay. And after that, we also need to, when we have done our first filter, maybe how to modify the system to do something else. And then the rest of the course, just to humor the embedded engineering students, there's a DSP in embedded systems, meaning what you can do with the small processor. Quite a lot, actually. Okay, enjoy the show. Any questions this far about the general stuff? Oops. Let me go to the first slide. There. Any questions? No. Oh, okay. This goes well. Whoops. So today we are talking about digital signal properties, and well, this was some drawing just I made just to avoid, you know, publishing somebody else's pictures. So what we are talking about here on application side is mostly about audio signal processing, since most of the systems actually do have audio properties, and if you have your own computer, you can even access them. I will probably ask the help desk to provide some, headsets for the computers here. Okay, so we might. So basically, let's take a closer look at this recording device here. What it is made of, where the signal actually comes from, and this does not really work. Okay, how many of you have actually done some analog electronics classes? I know you have probably have something. Okay, good, excellent, excellent. Are there electronics students actually also here? From the degree program of electronics? No? I was expecting, but okay. But anyways, so you know what that actually means. Yeah. So when we have a sensor like a microphone, it gives very small signal. It's just few millivolts peak to peak. You need amplifier. And then the next step is actually that funny box at the middle, which is a low-pass filter. Low-pass filter. Welcome. Glad that you made it. Okay, there are some nice, seats right here up front. Well, maybe we could actually move them here. Excuse me. Otherwise, you might end up being on video. We try to avoid videoing you today, but there will be actually one time we will try 360 videos. But you will get a, warning ahead of time to be prepared. Yeah, that's why we also have the records and online sessions. Okay, so sample hold is the second box there, meaning there's some sampling done, and then you actually need some filtering, analog filtering. Everything here is basically analog until the, this is still analog signal after the sample hold. Then we have the A to D converter. Okay. From oscilloscope, the signal on that point, on the beginning, looks small and also, please come in. There's plenty of, not that plenty of room anymore, but anyways, there's some seats. Would you pass on the seats? These are, yeah. There's also one seat here. And those tables are quite expensive, so if you break it, you will buy it. Okay. The reason why they are expensive is basically, no, I have locked that one. Only that one is open. They open up, go up and down. Okay, so we have analog signal. If you have an oscilloscope and take a look at it, it's very small, and usually there's a lot of noise on it. Okay, on that place, it's just bigger. The signal is amplified so that it will be bigger, but the reason to amplify it is the analog to digital converter has some range that it works, say 0 to 2.5 volts or something like that. And you want to basically take that small signal and amplify as much as possible without clipping. Okay, and then we need some filtering to clear the noise out. High frequency noise. That's interesting. Actually, when you sample the signal, sampling is done right there. Sample and hold. So sample, basically, a sample and hold circuit takes a sample at a certain time of that signal and keeps it constant, so that the analog to digital converter actually have some time to do the conversion. However, the sampling in time is done right here, this circuit. What the analog to digital converter actually does after that It just okay, it really does not show up, or is the next? Oh, okay, yeah. So there are these blue long lines are actually the quantization levels of A to D converter. Okay. So that's our whole range of A to D conversion range, and then the two lines there, blue lines, the distance basically means the least significant bit change. You cannot, observe it with a better resolution that least significant bit. Makes sense. Which means that that digitized signal actually is right here, that purple line, which is always the either truncation or rounding operation of that sampled signal. Okay, and same thing in pictures. So continuous time, continuous value signal, that's what we call it. The real life signals are continuous in time and value. It basically can get any value or at any time. Sampled signal has discrete time, but then it's continuous value, so it can still have any value. And then the digital signal is basically the same as the sampled, but with quantized value. Okay. And there's a cat. Yep. Okay. Basically, this stuff states just about the same, with a couple of markings here. I usually mark the sample time or sampling interval as capital TS, time of sampling. And then there's another concept called sampling rate, FS, capital F, small s. And basically it's just that the sample time is same as 1 over sampling rate. Very simple mathematics this far. Okay. When you are sampling a signal, you basically want to avoid so-called aliasing, and that's where the Shannon's theorem actually comes to. If you have taken the fundamentals of telecommunication, you should be aware of the Shannon's theorem. So you need at least 2 samples for each period of signal. Otherwise, this will happen. The blue one is a sinusoid, analog signal. And if you have a too low sampling rate, those red markers actually are the points where the sample has been stopped. You will actually, that blue, red circles show the envelope of what you will be getting out of the A to D converter. So it looks still sinusoid, but it has a little bit of problem of the frequency. Okay. So that means in earlier when we have this low pass filter, you need to actually prevent any high frequency components to go to the sampling stage. Otherwise you will see the aliasing. Okay. Yeah, quantization. For quantized value, which is basically what comes from the A to D converter, like the sound card of your computer. There's also the okay, I see there's a bit of problem with the symbol set of this computer compared to the computer where I made these slides. By the way, if you see this kind of mistakes on my slides, like in here, you can comment these slides. So just put comments, oh, okay, this doesn't show up well. I'll go and fix it somehow. Okay. Anyways, so the analog to digital conversion, it produces always an integer value. And then there's that quantization error. So the true value, it was the stopped signal compared to this closest or floored signal level of the A to D conversion. And then there's a couple of things like the quantization error. This is actually the size of the signal, or actually the signal value of least significant bit. But then the signal to quantization noise ratio. This is quite interesting. So that actually tells you how many bits you need to have your A to D conversion in order to achieve some sort of dynamic range. Okay, SQNR. For example, audio signal. So have you ever thought about why we have this 44.1 kilosamples per second standard recording the default for Sound Blaster or Sound Card? Well, that actually comes from this fact that human ear detects roughly between 20 hertz to 20 kilohertz signals. So you need to actually sample also the 20 kilohertz signals. So you need at least 40 kilohertz sampling rate, and that 44.1 actually comes from some history plus 10% for that anti-aliasing filter. Okay, and the rest is history. So we are still using this invention, which was done 1980 something. Okay, and so-called PCM quality CD signal sampling rate is 44.1 kilo samples per second. Then, okay, about the dynamic range. So how many bits you need? So basically listening music actually requires normally sound pressure levels in range of 20 to 100 dB. Okay, not continuous, this is peak. Okay, continuous 100 dB actually will destroy your hearing. So there's the 80 dB is the continuous threshold for losing your hearing. If you listen all the time with your headsets, more than 80 dB, you'll get hearing problems. And not old, but young. Okay. So in order to make the recordings with at least that 80 dB, well, that's 20 to 100 dB means 80 dB dynamic range, you need at least 13 bits. Okay, 13 bits is a little bit more than 8 bits. And 1 byte is 8 bits, so what is the next one? Well, 16 bits. That's why the CD quality PCM signal has 16 bits. That's enough. But you all know also that better audios always have 24 bits. Yes, it has more dynamic range. Is it better? Well, if you listen popular music, it doesn't make any difference. If you listen classical, well, it doesn't still make any difference probably, but it's easier to match the loudest peaks that they don't saturate. Okay. Okay. Then some basic fundamental mathematics about signals. There are some basic signals or fundamental signals that can help you generating, say, test signals to your, for example, filter design. One of the most useful is the delta function, discrete delta function, or Dirac's delta. Discrete Dirac's delta function, which is 1 at time point 0, otherwise it's 0. Simple signal, which has also analog counterpart, is the Dirac's delta, okay, which is quite useless in analog world. This is basically a fundament. This is just a this kind of mathematical concept. It is basically defined as it goes to infinity. Value goes to infinity at 0. Otherwise, it's the signal strength is 0. But if you integrate it, it still gives you 1 as integral. Okay, it's a little bit hard to understand concept, but anyways, in mathematics, this is used, for example, to derive the discrete delta functions properties. But anyways, still the same thing. 1 unit of energy at certain time. The next one is the Heaviside or unit step function. Okay, for those lucky ones who has been measuring some circuits with the oscilloscope, you have been using probably there on some lab sessions the square wave to test a RC circuit. Square wave is more or less the same as having a periodic series of Heaviside with some time delay. So you turn it on, turn the signal on with Heaviside function or the unit step function, and you can actually turn it also off by subtracting a Heaviside function. So that's how you generate pulses that you can, again, you can use those to test your system. And there's also something in between this delta and Heaviside is basically that if you take this step function and make a time delay of 1 and subtract it immediately here, you will get actually just delta function. Or, well, that summation is kind of funny also. Okay, then there's that delta function versus any signal x of n. Okay, this basically says here that you can describe that signal, any arbitrary signal, as supercomposition of the signal's different points. So that actually, if you have a linear system, then you can test the system with the simplest function, which is the unit delta function, discrete delta function. You can use that to test the system, and it basically behaves similarly also with any arbitrary signal. So that's basically foundation of why we can why we can make digital filters. Okay, more concept fundamentals. Periodic signal. That's a lot of math. No, not much of math, but actually it's quite a lot. One simple sentence here. If you have a situation that x of t, so this is any signal, is the same as x of t plus some constant time t, then you have a periodic signal. For example, sinusoid. In sinusoid, you basically have that 2 pi ft, so the base period is there's 1 over f time period. And the signal just repeats itself at that interval. Simple. Nothing is simple with the sampled signal. The same definition, but then you, instead of real numbers for t or any value for t, you can use only index values with integers. So basically it means that the previous signal, when you sample it, it's probably not any more periodic. What it actually means on spectrum, okay, have you heard of, I think, is the concept of spectrum, are you okay with that? Since I have no idea what you have been studying here before. Okay, but let me explain what that one actually means on the spectrum wise. Okay, so basically on spectrum, yes, you need binoculars to see that. But don't worry, I'll also take pictures of the whiteboards, of those on the internet. So if we have a continuous time signal, sinusoid signal, and there's the frequency in hertz. If you have a poor sinusoid signal which started, from -infinity and then goes to the end of the world, you will have single peak here. Right, just like in telecommunications fundamentals. Okay, but if you actually happen to sample this one with almost any sample rate, it does not quite match exactly. If it does match exactly, then we'll get just one single peak here. If it doesn't, the sample actually have also, okay, this is also might be familiar with the telecommunication, you get side lobes, right? So what you get is actually that kind of side lobes, just because you started sampling it. This is fundamentally a similar process what happens when you're starting to transmit data on telecommunication lines. You have this analog, really nice poor sine, then you start hitting it with square waves in principle. You will get side lobes. Okay, so that's the sampled spectrum. And this one here, which doesn't show up, was the original. Wait. Okay, there. Good. So after sampling of the signal, it's not necessarily periodic, but well, at the exercises you will see the effect there. Okay. That's nice. I actually made the frequency space slide myself there. Okay. Are you familiar with this one? Anyone? Does it ring a bell? It's about the Fourier series. Okay, that basically says that you can describe any periodic signal with the Fourier series, and this is just a sampled version of it. Okay, this should be capital N. Oh, small n, but capital T. By sampling a Fourier series, of course, you get the basically the spectrum, and the spectrum components are A0 holds the energy on or power on the 0 hertz, which means DC offset. Okay, then AN and BN carry information in two phases, 90-degree orthogonal phases. Okay. All right, more concepts. Random signal. What is random signal? Basically, any process that produces unpredictable values is a random process. So, so these lectures are quite random, right? In that sense. Basically, the random signals, I would say most of the signals from nature are random. There are some signals which are not random, only few signals. One natural source of those are pulsars. Have you heard of pulsars? Okay, in astronomy, those are the basically leaking stars which are rotating and they are sending a pulse in very constant frequency. That's almost non-random. But for example, wind noise in microphone, it's a random signal. That causes some trouble. And this is caused by small-scale turbulence or mechanical structures. Then in electronics, there are a couple of things that will be there. There's shot noise in electronics. If there is current, then there is also noise caused by the charge carriers. So current is actually flow of electrons. Electrons are quantized charges, so it means that you also get some quantization noise there. Every time when you have current flowing, you will have shot noise. Unless you have the current, the smaller the ratio of the shot noise to the signal will be. Okay. Then Johnson noise in electronics. That's basically, again, we have these charge carriers are electrons and, well, some in, yeah, they can be also the holes. But anyways, electrons and and that's Johnson noise is the random thermal movement of these charges. What you can do about that one? Not much. In scientific laboratories, you can actually cool them down, but not in real life. All right, those are the natural sources. So basically that one comes in the signal, and these are already piling up from the electronics, starting from their sensor. So you always have some noise. Two kind of processes basically in nature. One is the flipping of the coin. It happens or doesn't. So you got Poisson's distribution in small number of that kind of events. And then there's also the normally distributed random numbers. Fundamentally, all random processes will show up as normally distributed random numbers when you get enough of samples. I think that's something that some theorists may have found out somewhere. Anyways, okay, both of these random signal types are quite important for you. So Poisson distribution is very important for digital signals when you are sending bits, okay, or bytes. The error there is Poisson distributed. Okay, then the rest of the word is more or less normally distributed noise. And okay, statistical analysis. That's one kind of thing that you can do easily with your signal to see what kind of distribution is actually follows. The left-hand side, well, there's only 1,000 samples, so it looks like that. And well, I had quite small lambda, meaning the most. That's the what is that called? Odotusarvo. The value which is mostly expected. So we're expecting number 2 and start flipping so-called coin, you get zeros and ones and so on. Okay. Then the normal distributed random numbers, actually, that will be following the Gaussian shape bell curve. That's basically the distribution of those the values of the signal or the noise. Okay. Cross correlation. Earlier we had a noisy kind of thing. With noisy signals, there is a tool called correlation, which actually can be used to find out if there are any signal or very noisy data or some other applications. So basically this is the first real tool which you can already apply. Well, maybe not this week, but you know, I have one of the project topic is sonar, acoustic radar. You can do it with MATLAB, semi-random signals, and some correlation analysis. And it's simply simple calculation. You take the wait a minute. Do I have an error here? I might have an error here. Or do I? I need to check it. Anyways, the correlation. No, it's okay. Yeah. The correlation basically means that you have two signals, X and Y. The samples of X on left hand, there's samples of Y on right hand. Then you start basically shifting the other one over the other and calculate the sum of the products. Basically, on this point, I would say even the left hand and right hand signal would get the most out of that product, since, well, we have the thumb is basically multiplied with pinky, but those will get smaller ones, but the basic three other fingers are about the same length. So this position or time lag n would give you the best match. And then this will be less, since you are leaving some, there are no fingers here, and then that one. So this would probably pick up something like that. So basically, the cross correlation gives the best match or the location of best match of two signals. And this we can then use, for example, for searching for some features on the signal. Okay, now I need to draw again. Okay, now this is time-based. Two signals. I will leave that one for the end. So, for example, if we have measured kind of noisy signal like that, and we want to know in which location we could find that kind of feature. So this is, for example, our y. This was x. So basically we do the correlation. So this correlation would get the maximum wherever we have the same features on the other signals. That would give the maximum peak basically on this distance from here. There. It has some noisy, but the correlation would get highest on that location here, which is fundamentally the same distance as that one. And this is no magic, it's called engineering. So matching a known feature from unknown signal. And this one has quite plenty of applications, including the sound radar sonar. You send a beep or a chirp signal and then start listening it. What you will hear is very loud signal on the first when it starts going out, and then you hear the reflections which are covered with noise. Okay, quite like, you know, watching a U-boat movie. Bing! Okay, and then matching this time will give you the depth of this submarine, or, well, if it's open, you know, open in the air, you can quite easily to detect, say, flat objects with a very simple setup. Okay. Then there's another one, basically it's autocorrelation. Autocorrelation is correlation of signal with itself, which means that if there is a repetitive section on a signal, it will show up the peak on the repetition time. Well, self-similarity. For example, that sonar. Sonar signal. The signal strength, and when it goes out, first you get the big peak here because, well, you have the loudspeaker or piezo, basically the microphone. You get directly that sound from the source to the microphone, then it goes out. Then there's a reflector here. Any surface, basically, sound bounces back to the microphone, much smaller, but somewhere in there you will have self-similarity. Since it's from the same source, it looks like the same. So basically doing the autocorrelation should give peak somewhere in there. Should. Okay. Something about the calculations again. The correlation calculation, if you do the full cross correlation calculation, it basically you need to go through all of the data. So for each time lag, you will make actually one time. You make multiplications n times, the sample length times. So the full correlation from minus n to n takes 2 to the power of n to the power 2, multiply, add calculations, and they will take time unless, well, of course, we have plenty of power here. On the other hand, you can do everything also on the frequency space, which is nothing to be afraid of. You just simply take Fourier transform of the signal and multiply it with the complex conjugate of the Fourier transform of the other one, and then, well, then you take the inverse Fourier transformation. It's simply as that one, and that's basically the fundamental thing on which you need to just remember if you ever need to do it. The Fourier transformation, inverse Fourier transformation are just functions that you will call, and the data here you would either make yourself or record from some source. So this is quite technical thing that you can do. But this one actually saves time because there's so-called fast Fourier transformation. Do I have anything about that? No. Fast Fourier transformation, which saves time. If you want to know more about fast Fourier transformation, it's very nice practical theory done in 70s by Cooley and Toki, and well, it's entertaining to see how it's done, but on the other hand, also a function in any math library. Okay, yeah, that's just that example. Another kind of useful tool, and not just kind of, since convolution is the fundamental, it's the basis for any digital filtering. So convolution between two signals, it's defined like that, which basically, okay, let's take a look. So the correlation was somewhat similar, but you have both of the signals are going same way time-wise. On convolution, for some reason you flip the other time axis. So instead of correlation and shifting, you would actually do time reverse on another one and do the same operation. And that actually comes from this fact where we would need it. There should be, Z transforms. Okay, that'll do. From Z transforms, which is just an extension to Fourier transform. Don't worry too much about it. There are some books, actually, those digital signal processing books. Look at those if you need some more information, more detailed things. But we will be practicing also about this, some of those transformations. Okay. Well, it appears that if you have a multiplication of frequencies, why would you like to have multiplication of frequencies? Maybe this is the reason. Basic filter property. That's frequency. That's the value. Okay, if your signal spectrum would look like, for example, like this, something. Just example. Signal spectrum. And that's something you don't like. That's noise. So we say, okay, maybe this one here, it's noise. How to get rid of that noise in frequency space? So this signal spectrum is practically Fourier transformation of the signal, which is a function that you would use, which produces Fourier transformation. How about this one? You multiply it in frequency space by that kind of window. So this is filter, we'll just call it properties. Multiplication with those in Fourier space, in frequency space, will produce you the spectrum you want from the signal. So it follows like that, and then it goes basically flat here. Gets rid of that part of the spectrum where this noise was. Okay, actually what it comes to is the multiplication in frequency space is the same as convolution in time space. Okay, so this is quite practical now. What you need to have to do filtering here is have the system transfer function known. Then you do the, well, that's the system transfer function. The inverse transfer function would be the this impulse response actually later on. So that calculation here, exactly this what we did, is the same as the convolution. So convolution is fundamentally same as filtering. Okay. More definitions. Earlier we had the quantization signal to noise ratio. Telecommunication basics again. The signal to noise ratio is defined as the 10 log 10 power signal divided by power noise. Okay. Which actually end up also into this. Ooh, that's a nice sound. On the other hand, 100,000 other people has the same sound, so you might actually change it at some point of this course. Okay, so signal to noise ratio can be also if we have so-called random signals, as we usually do actually, is the signal variance divided by noise variance. So statistical stuff, and this is where you need some statistics. It's quite useful tool. For example, on estimating the signal to noise ratio of a system, or the sensitivity to noise of the system and such kind of things. So this is called engineering kind of thing. Okay. More stuff. So whose head will explode in 5 minutes? No, nobody. There's plenty of small things coming up. And you know, we have convolution, we have correlation, now we have power spectrum analysis, we have the random processes. What else? We have the sampling. How does it make sense? Eventually this afternoon, if anyone comes here, on the MATLAB exercises, we will see what these actually mean practically. Okay. However, this power spectrum describes the distribution of signal power into frequency components. That's a definition. And yes, it can be calculated by Fourier transformation of the signal. So power spectrum is simply Fourier transformation of the signal, and that's the norm, second norm of it. So you multiply it with a complex conjugate. So that one gives a power which is, well, given how does power actually will be plotted usually, or given as decibels, right? As decibels. The unit is usually decibels, since in signal processing you always or most of the time know also some reference point. Okay, but that's the power spectrum, the definition. And yes, discrete Fourier transformation is for sampled signals, and practically it's the fast Fourier transformation to do the this DFT. And that's the example of a sinusoid signal. Remember, the sampling of sinusoid or periodic signal is not anymore periodic necessarily. So this is the spectrum sampling rate of 1000 samples per second and 50 Hertz signal, exact 50 Hertz signal calculated in MATLAB kind of system. Well, that's its octave plot actually. And yes, there is a, oh, that's funny. Excuse me, would you push the that curtain a little bit down? I think it's the button next to the door. That one, yeah. Yes, thank you. Now it shows up. Sorry, didn't notice that before. So okay, so 50 Hertz has a peak, but then there's also this envelope. Comes from the fact that this is a sampled signal. It also actually comes from the fact that, okay, I used such certain amount of samples here. Some more stuff on exercises, I think. Spectrum analysis. The previous one was actually single spectrum, which has power in decibels and frequency in hertz. Spectrogram actually is a nice tool for seeing signals which has varying frequency. Okay, so previous one has just one sinusoid. This one here is a chirp signal. You know the chirp. It has the basically the frequency is varying just like that red line there. So it starts basically from 0 on time and 2 seconds I see, and then basically the maximum frequency here 500 Hertz. Yes, 500 Hertz because of that 1000 Hertz sampling rate. Okay, 2 samples for each period is needed, so the highest frequency in this case was 500 Hertz. Okay, and yeah, you got that kind of thing. So it shows linear change of the frequency over time, and that's chirp. Okay, excellent. Now we have some time for questions, comments. Was it fun? Do you ever come back again? Take a look at this presentation yourself. There is a questionnaire, anonymous questionnaire. Please fill it up with some, thinking and maybe reviewing some of those books and such kind of things. Don't go yet. Take a look at the how well did I actually give you some information here. This is the way I taught you today on the lectures, and that's basically for me to see how well did you listen me, or did you listen me, or did you play with your mobile phone, or yeah, did you find any those what are those Go characters here? All right, so anonymous questionnaire, just for you. There are also the correct answers, if you need to know. And then, help me improve this material. I need feedback. Give the feedback using commenting tool to this document. Okay, that's the way I can actually then fix it to the document itself. Questions? Absolutely no questions. Okay. So it looks like we have a little bit longer lunch break. So we will be continuing at 12 o'clock, same place on the LabVIEW, oh not LabVIEW, MATLAB laboratories. And if you have computers, download Octave on that one. Octave. You will be needing that one since we have a little bit more students here than computers. Okay? Good. Back sharp at 12 o'clock. Yes.
Participate today, this evening?